Alright, welcome back. In this particular video you are going to learn different kind of neurons. Okay. Alright, so I'm sure already you are familiar with the very first artificial neuron, that is perceptron. So I'm not going to discuss about that thing, which contains basically unit step function or binary step function, which produce a range of two different classes from -1 to 1. We already discussed about that thing, so I'm just writing it down for your reference. Okay. Next neuron is sigmoid. Alright, just to be clear, all these neurons has only one specific difference, that is the activation function they are using to produce the final output. Okay, till net input, the content which we are feeding, the value of z is same for each of them. The kind of calculations they're doing at the activation stage are different. Okay, so the first advanced neuron was sigmoid. Okay, what it does, it creates the output value between a range 0 and 1. Okay, so this is the graph, how it works, and this is 0, this is 1. What it does, takes the input, and the more it will go closer to 0, sorry for this, all these stupid. Alright, the car will look like similar sort of things. It is pretty much similar to like shape is. Okay, so at the point 0 or greater than 0, it will become, it will tend to shift toward the class 1. If it is pretty much less than 0 or it is far negative, it will be 0. And once it has reached close to 0 or greater than 0, it will move toward 1, and it will be 1 through that kind of till infinity, whatever it is getting. Okay. So the equation for this sigmoid function is, suppose this is t to z equal to 1 by 1 plus e to the power. Right? So we'll have this practical implementation in some time, and you will see it if we increase the value, like the negative value will have for this z. Alright, just to be sure, this is z. Okay, this is theta z. The value of z, if it goes to a negative, bigger negative, the value of this whole function will be 0. And if it moves toward positive, you will have max value till 1, and close to 0 plus minus a little bit of shift, it will have a smooth ride toward 1. If you remember in each step function, we had a sharp rise, like starting from -1, and if it is 0, it will straight forward jump from -1 to +1, and then it will go. In this particular case, you will see it's a smooth ride to +1. Right? So this particular function is being used inside sigmoid neurons as an activation function. Okay, so the output value would be between 0 and 1. Okay, so alright, so next type of neuron is tang. Oh, any great. What it does, let me write down the output it between 0 to 1, minus 1 to 1. Okay, just writing it down for your reference. In this particular neuron, what happens, the output value from the activation function will range between minus 1 till plus 1. Okay, so the equation for this is e to the power x minus e to the power z minus e to the power negative z plus e to the power negative z. Okay, this is kind of simplified equation, and it is same as, like, you will see some places where it is using little bit of different kind of next stage of this whole equation is minus 2z 1 plus e to the power minus 2z. Okay, these are the same basically. And if the value of z goes toward negative, far negative from 0, the minimum value will have minus 1, and if it goes toward right, far positive, the maximum value will have plus 1, and in between minus 1 and plus 1, the value of z, it will have a smooth right till from minus 1 to plus 1. Okay, let me sketch it. Alright, so this is suppose this is minus 1 line, or plus 1 line, this is minus 1 line. Okay, plus 1, minus 1, and somewhere this is minus 1, plus 1. This is value of z, this is z. Okay, for this tang function, the value of the activation function will be something like that. If it is far negative, beyond minus 1, it will go like this. From this point, it will start shifting smoothly toward. Okay, it is not like that, right? So this, and then it will go on. Assume this is straight, okay? So these similar sigmoid loading function, but it will start shifting from minus 1 lowest value till plus 1 highest value. Okay? So the output from these kind of neurons will have a value range from minus 1 till plus 1. Okay, this is the equations. You can keep it in mind for future calculations, but definitely in our first implementation, before our first implementation, we'll try to implement all these activation functions in a kind of matplotlib graph, so that you will have these visualized picture in your mind, how each and every neurons which are particularly using these set of activation functions are producing their output for the next layers. Okay. Alright, so the next big thing is that rectified linear unit. Okay, so what it does, it produces a value range between 0 till 1. Alright, let me tell you one thing. This is the most widely used type of neural network at this point of time. Most of the implementations they will use these ReLU activation functions for the network. So this is very important. Okay, the equation for this is not that much difficult. It is simply like equal to max of 0 or z. Alright, just to clarify, the equation for ReLU activation function is either 0 or z. Okay, if the value of z is less than 0, then 0. If it is greater than 0, then z. Okay, so this is z, this is, to implement these equations, the value would be something like this. It is going till 0 and then this. Okay, and maybe this is 1. So if the value of z or net input is positive, then the output of this activation function is the same value as net input. If it is negative, then it is 0. Okay, so the curve is something like this. Alright, so this is the kind of most widely used activation function. And later during implementations we'll have some understanding about hyperparameter tuning and check it like which neurons are performing better. Normally sigmoid will have slower learning and attention ReLU will have much faster learning than sigmoid, and similar sort of considerations we have to do to get the best result out of our networks. Okay, you can try with the combinations of sigmoid, tan and ReLU in a single network. For each and every different layers you will have different activation functions. However you want to try, I will teach you the process how to use them. Then you can play with them. Okay, this is the graph for ReLU output, and this is the rectified linear unit activation function, and the value will range between 0. Okay, so we're talking that this is the ReLU activation function, and the value of this ReLU activation function will range between 0 and the z. Sorry, this is not correct. Okay, and it should be greater than 0. Always greater than 0. Okay, so by this time you have clear understanding about all these activation functions or different kind of neurons. So there were some other advanced implementations of neural networks. Especially on ReLU side, they call it leaky rectified linear units or parameterized rectified linear units. Similar sort of things. What they do, like in the place of this hard 0 for leaky okay, what they take in the place of this 0, they take max of 0.01 Z and Z. Some compromised value of Z, like basically divided by 100, thousands, and blah blah blah, whatever the fraction they want to take for the negative values, and the Z values if it is greater than 0, and if it is parameterized like P ReLU, then it would be kind of max of alpha Z, and you will have some controls over this alpha. Okay, so these are pretty advanced kind of activation functions or neurons. Normally we don't use them very frequently unless situations comes and you have to consider them. But this is just for your understanding point of view, in case you are curious and you have heard about this term like leaky ReLU and parameterized ReLU. Alright. Okay, so all these implementations or activation functions we are going to try in code in some time, and you will have complete understanding and the visualizations how they are going to take the input and what would be the final output in the graph and plot itself.